Hey everybody, welcome back to chemistry and welcome to officially your second semester. We're going to start this semester off with a unit called gas laws, where we're going to spend some time investigating all of the different behaviors of gas and how they impact one another. So let's go ahead and start today's lesson off with a quick video demonstration of what is called Boyles Law. So what we're going to notice here is we have a semi-filled balloon in a vacuum chamber. What is happening is the switch of the vacuum chamber is put on. So let me pause the video. When we flip that vacuum chamber on, what's happening within that vacuum chamber? Okay, now remember we've seen this before, talking a little bit about vapor pressure and boiling, but when we flip that on switch on, okay, what happens is the air from inside of that vacuum chamber is removed. Now, what we notice is that as that air is removed from the inside, the balloon is expanding and it's going to continue expanding. Now, what is going to eventually happen is if we flip that switch off, the air is let back into that vacuum chamber and our balloon decreases in size. So let's go ahead and jot those observations down, okay, for our notes sheet. So, okay, we saw that we had a semi-filled balloon, okay, that increases in size when the vacuum is turned on. Okay, and then we can also just note that it decreases in size when the vacuum is off. Okay. Now, something that we're going to talk about in this unit is the manipulation of conditions or variables. And so we are going to just I'm going to demonstrate it for today, but in each of our lessons for this unit, I am going to ask you to consider which conditions are being held constant. Now, some stuff that was changed, if we think about this during this experiment, was external pressure, or the pressure inside of that vacuum chamber, and then also the size of our balloon, the volume of that gas. What kinds of things were held constant? Well, in the vacuum chamber, okay, we had temperature held constant. Okay, the temperature was held constant, right? There was no shift. We didn't heat it up. We didn't cool it down. We didn't add heat. We didn't remove heat. And also the amount of gas, right? The amount of gas within that balloon. It was pre-filled. They closed it off. It was sealed, right? It expanded and it went down, but the amount of gas in there did not change. Okay, so temperature and the amount of gas were held constant in this experiment. Now, this leads us to kind of a quick discussion about pressure. And I mentioned this in vapor pressure, the unit, where we were going to talk a little bit more about all the different units of pressure. But I did want to just kind of point out or discuss a little bit about what's happening when we remove that air from the inside. So there's really two types of pressure that we need to consider in this experiment, okay? There's the external pressure, the pressure that's being pushed onto the balloon. It's created by the air pressure around us. And then we have the internal pressure, which is really just the gas particles. And when you think of internal pressure, it's not really pressure so much, but it is pressure, but it's caused by those gas particles colliding with the interior of the balloon. So it's really those gas particles moving around. So we're not really going to focus heavily on the internal pressure because we're not really adjusting that too much within this Boyles Law experiment that I want to kind of talk about. But our major change that we see has to do with our external pressure. So in a vacuum pump, okay, the air is removed from around that balloon. So what do you think happens to that external pressure caused by the air? So if we remove all of the air, is that air pushing on the balloon anymore? Okay, or is it decreasing? And so if we kind of remove all of that air out, then we no longer have that pressure pushing downward on the outside of the balloon. So in the vacuum, okay, air is removed. Okay, when the air is removed, the external pressure decreases. And from there, what then happens to the size of our balloon? So we take the air pressure out, there's no longer that pressure pushing downward, and so that balloon expands or it gets bigger. So the volume of the balloon increases. And this is essentially Boyle's Law. And again, we'll pop back down to Boyle's Law in just a moment, but I do want to take a moment to just talk to you a little bit about what is pressure. Okay, talk with you about what pressure is. So pressure is going to be the force that is exerted by the substance per unit area on another substance. Okay, so when we're saying external pressure, we're talking about how much pressure the air is pushing downward per unit area on that balloon. Okay, we can think of calculating pressure as force over area. So for example, if I were to apply my body weight onto, let's say, onto something small, right, the pressure being exerted is much greater than if I were to stand on, let's say, my table, which is much bigger. Okay, so the smaller the area, I'm still exerting the same amount of force downward. My weight doesn't change. The bigger the object, the less pressure it feels. So we have lots of different ways that we measure pressure. We already are familiar with one of them from the vapor pressure unit, or from talking about vapor pressure, which is kilopascals. Okay, and so standard pressure, right? We've talked a little bit about what that means, but standard pressure is going to be 101.3 kilopascals, okay? And that unit can be converted, and the next type of pressure that we primarily use for Regents level chemistry is atmospheres. And so 101.3 kilopascals is the same as saying that we have 1 atmosphere of pressure, okay? So this is atmospheres. Both of those are listed on your reference table. Again, reference table A, I believe. There are sometimes a couple other units of pressure that we will see. Okay, one of those is millimeters of mercury. Okay, and so 101.3 kPa is equal to 1 atmosphere, which is equal to 760 millimeters of mercury, which is equal to 760 torr. All of these are just different ways that we can measure pressure. And I do want to point out that, again, we really heavily focus on just these 2 types of pressure for this course, but some of the problems that I might bring into class may or may not use millimeters of mercury or torr, so I did want to point those out as well. All right, so back to Boyle's Law. Okay, as external pressure decreases, what happens to the volume of the balloon? What's going to happen to that volume? So again, as we take away the air pressure, the volume of the balloon increases. Okay, increases. What happens to the speed of my particles? Okay, and this is kind of a trick question, so I want you to really think about it. What happens to the speed of my particles? Okay, if you said that they stay the same, then you are correct, right? Remember, we measure the speed of the particles as the average kinetic energy or the temperature, okay? And again, we said temperature is constant in this. They're not moving any faster. It's just if the external pressure is removed and that gas particle hits the inside of the balloon now, it's going to cause it to expand. It's not limited by that external pressure. So this leads us to Boyle's Law, okay, to Boyle's Law. Let's go ahead and finally officially talk about Boyle's Law. So Boyle's Law states that if temperature is held constant, okay? When pressure decreases, okay, volume increases. Or you can think of that vice versa, right? As pressure increases, volume decreases, right? If you're applying a lot of pressure on something and it's pushing down, then your size is going to decrease. Okay, this is Boyle's Law. And again, it does matter. Temperature does need to be held constant for this to happen, but they are indirectly related, okay, or inversely related. So they have what's called an indirect relationship, right? As one increases, the other decreases, and vice versa. We can represent this mathematically, okay? And so our equation for Boyle's Law, okay, is P1V1 equals P2V2. So P represents pressure, and V represents volume. Okay, so the pressure and the volume multiplied should be a constant, right? So P1 times V1 is equal to P2 V2. So if I change my pressure, then it's going to change my volume. So let's go ahead and represent this mathematically here. Okay, and to just kind of highlight what this would look like. So we have a problem here. So initial conditions, P1 V1 versus P2 V2. So we have P1, 1 atmosphere times 1 liter is equal to 2 times X volume. So in this case, if you think about it logically, we've increased our pressure, our volume needs to decrease, and we end up getting 0.5 liters, okay? And so that is Boyle's Law. Now, I would say the one tricky thing about Boyle's Law that we do want to consider is we do want to kind of think about what this would look like graphically, okay, what this would look like graphically. So we're going to go ahead and we're going to label our graph. This is going to be a pressure versus volume graph. So pressure versus volume, okay? And when I sketch this out, I want you to sit and really think about why I do it this way. So first of all, they're inversely related. They are indirectly related, so they are going to require, right, as one increases, the other decreases, okay? But our graph doesn't end up being a straight line. It ends up looking like this, okay? And so I want to point out that we are going to end up with an exponential relationship. And the reason being, right, volume will never equal 0, okay? And pressure will never equal 0. So we will approach those limits of 0, but we're never going to actually reach them. And so we end up with this, okay, exponential relationship, okay? And that, my friends, is Boyle's Law. This is the law, again, that investigates the relationship between pressure and volume of gas particles, okay, as long as temperature is held constant. All right, everybody, I will see you guys tomorrow. Have a great rest of your day.